Good. Okay. So I like to start by putting a picture right in. And in fact, what I like to do, I'm going to insert probably, I'm going to insert the picture of the DNA ladders. Okay?
Okay.
And so I like to, because I like to have it right in front of me. I like everything like right in front.
Mm-hmm.
So then I'm going to insert another picture. And what I'm going to insert is my gel picture, which I should be able to do. I'm just going to navigate through some of this. All the crazy stuff I keep track of on this computer. And there's one of the gel picks, okay?
Yep, that's the one I'm using.
Okay. So pretty, and I'm just going to resize it just to make me happy so everything fits in the same screen. So now we've got everything there, okay? Mm-hmm. And you can kind of see, if you look at the orientation of the DNA ladder, which is right here, okay? So the DNA ladder is, in this particular case, is in the rightmost area.
Yeah, it's also upside down, it said.
Yeah, it is, because look at so compare, we're using the phage lambda digest, okay? So this is the phage or phage lambda, okay? And then you could see it's got 1, 2, 3, 4, and then 2 are separate. So we've got, notice, here's our 1, 2, 3, 4, and then 2 are separate. So it's inverted. Mm-hmm. So if you want, you could do this either of 2 ways. Now the reason for this is I like to have the well at the bottom of my picture. So if you kind of look, in here, right where I'm highlighting these cells.
That's the well line.
These are the wells. In the phage lambda picture to the left, the well is actually at the top. And it's really a matter of convention. It doesn't really matter which is which. It's just you kind of have to remember which is which, okay?
Yeah.
And the reason for this is that the convention of where to put the well in a picture depends on your background and training. People who are trained in chemistry and biochemistry labs generally look in one direction. People who are trained in biology labs look in the other direction. And it's just a question of where everybody was trained and how they like to do things. So all you have to do is remember which direction. Now, since our phage lambda is showing it in this direction, just to make it, I'm going to flip this picture so that it matches. And I should be able to do that here. We're going to look at rotation. I should be able to flip it in the Y direction, 180 degrees, and there you go. Okay, so now you can see how the phage lambda picture in our DNA fragment graphic matches up. See, here's our 4,
yeah,
and then 2, here's our 4 and our 2, okay? And so what I did here, and this is a little bit different, so now you just have to remember, because we flipped it, your loading well is up top, okay? So now we can measure, and now some people can't see. There are 2 ways to deal with identifying the loading well. One way, first of all, we have to be able to draw lines on this. So I like to insert illustration, and then you can kind of pick what shape you want, and I want a line. And so one way you could do it is actually draw a horizontal line all the way across the gel. And then, of course, you can't see it. So what you want to do is make it a color and a thickness you can see. So I'll make it that. So now you can see it, okay? So you could do that. And that's a fine way to do it, except I often, a lot of people have difficulty figuring out where that starts and stops. So what's a really easy trick to do is if you like this, then do it that way. If you don't like it, I'm going to delete that line. And now I'm going to insert another line, go to my shapes. Here's another line. And all you do is start measuring from the top of the picture. Because that little bit of difference between the loading die and the top of the picture, or the loading cell in the top of the picture, is really irrelevant for the distance that the band travels. Okay? So as long as you're consistent with your starting point, that's all that really matters. So
Okay.
what I'm going to do is I'm going to measure this, and you measure it to the leading edge of the gel. And you want to make sure it's straight. There you go. And of course, I'm going to go back and change my line type here. Let's see. Let's get a nice thick one that you could see. All right. So then what we're going to do is we're going to start on the right-hand side of this Excel spreadsheet. If you look at the size and position of the line, you could see on the right-hand side, it tells you basically they call it the height, but that's because it's a vertical line. But you can also change this to inches. It doesn't really matter if you're dealing in millimeters or inches. Somewhere in the options, you can change that into millimeters, centimeters. You can even do it in miles if you want, although it's a very small number. So what we know here is that distance is 2.12. So I'm going to pop that in there. And what we can put this in as distance traveled. And then over here, we can put number of base pairs. And we know that that first line is over here is 23,130. So we go 23,130. Okay? And then you can draw another line, but I kind of like to do it a little cheater's way. And I just bring the line down, and notice Excel in its infinite wisdom automatically updates the size of the line. So we now know this is 2.33. And we know that we've got 9416 base pairs. And just to make life easy, I'm going to go ahead and fill these in, 65, 57, 43.
Do you want us to plot the phage lambda on the graph as well?
Oh, yeah, absolutely.
Okay.
So so again, I'm going to go through here, go to the next one, 2.56. Go to the next one. And again, you just got to try to keep it straight as you can. Why won't we do that? And it's what, 2.82. And then the next two sizes are 23, 22, 20, 27. And in this case, we'll just keep going. Oops, I forgot to read it. 339. And the next one is 361. And if you notice on our example graphic, notice that both 564 and 125 base pair fragments do not show up. However, on ours, you can see that very faint line down here
Mhm.
right there. And in fact, that is the 564, which is at 571 for our, so that's 564 at 5.71. And the reason for the difference is our example here of the phage lambda is done on 0.7% agarose, and our gel is run on 1.2% agarose. So the higher density of agarose in the gel gives us a little bit better resolving power. So once we've done that, all we have to do is insert a graph, and I am just going to highlight. You do that, I'm sure you know how to do this, you've done it. Insert a graph. I always love to, you know, you have to be really careful with Excel because sometimes their defaults really don't don't work the way they ought to. So what you want to do is make sure that you get to the scatter plot. It's got to be an XY plot. I generally do it just like that. And if we take a peek, real simple, of course, this becomes our standard curve. We want to insert, let's see, where is it here? Format axis, I think we can, oh, blast. I really sometimes dislike properties.
It might be up in add chart element.
Ah, good call. There you go, axes. Primary horizontal, in our case, this is base pairs. Where'd you go? Oh, come on. Oh, duh. There we go. I see what I did. Vertical. So there's our base pairs. And then of course, we'll add our axis title on the vertical. And in this case, it's going to be distance traveled in inches.
Okay.
So always good to make sure that, you know, you have your, you have everything labeled properly. Then of course, what we've got here, and you can kind of see that the smaller fragments travel longer distances. Now, I look at this, and one of the things here is I look at this and look at what's on the x-axis. It's total number of base pairs, right? And distance traveled is in the y-axis. Now, if we're to look at, in our picture, what we want to know is what the size of these bands is. So if we take a look at this, what are we going to measure? We're going to measure distance traveled, right?
Yeah.
So when you write the equation of a line, it's always in the form of y equals mx plus b. Okay, at least for a straight line, right? So what this tells us is we're measuring distance and want to know base pairs, which means we really have our axes backwards here. Because
Okay.
what we want is we want to have on the x-axis, we want distance traveled.
Mhm.
So what you want to do is reverse these axes. And so we ought to be able to do that. Format plot area. Come on. Oh, I hate the new version of Excel. Nothing's where I'm used to in the other types of programs I use. So, well, shoot, I'll just do it like this. So what we really know is we want to swap these out because we want our distance on the x-axis. Now we can insert our scatter plot. Now we have a nice scatter plot here, and I'm just going to replay this, insert titles, primary horizontal. This is, of course, distance traveled in inches. Oops. Let's make this a little bigger. Put another axis title in, primary vertical. Base pairs. In fact, I'll even label it. That way it's nice and easy to see. Total number of base pairs. And now comes the fun part, which of course is here we want to create a line, okay? So all I'm gonna do is I don't like to create the line here. You know, if you can put one in, certainly, but all it does is connect the dots, okay? So what I tend to do is once you select those data points, if you right click on it, you can add a trend line.
Okay.
And then now notice, look at our trend line and also look at the options we have in the right-hand pop-up box here. First of
It needs
all,
to be exponential.
obviously it's not linear, right? Okay, so we can certainly look at exponential. You could look at logarithmic. And I encourage you to just look at and see what it looks like. You know, look at what each of the curves looks like. Polynomial, and of course a power function. And boy, look at that power function, fits perfectly. A really nice thing to be able to do is down here in the options, display the equation and display the R squared value. Now I'm going to lift this up a little bit here. And I'm going to increase our size to make it easy. Now, you can then go back to our trend lines. And you can go through and say, okay, here's our exponential function, here's our linear function. And again, for each of these, you can go through and you can add your particular line to it. I always suggest that you pick the one with the best R square value, and you can see R squared is really, really high here. If we were just to add an exponential function, which is a negative exponential function, and here's what I'll do. I'll just give you a second on add another trend line. Let's use exponential, and let's go ahead and display the R square values. You can kind of see the difference between the R square value. The higher the R square value, the better fit of the line.
Okay.
So you can kind of see that the exponential, the power function is actually better than the exponential function. But it's really entirely you know, how you want to do it. I mean, it's really how, and I'm going to go ahead and get rid of that second box here in a minute. There we go. So, but it's really kind of up to you to decide how you want to attack this problem. I always, in the laboratory, when we're doing this at the graduate level or research level, you always use the best R-square value, because that's going to give you the best estimate for your unknowns. Now, of course, what you've got here is, now we know that our first line here is, and by the way, this is, you can see pretty clearly, this is the lane that has two, I'll put both restriction enzymes, and the first lane, if we click on it, the first band, where's our width? Size and position. So is 3.02 inches. And the second band, which again, way down here, is 5.14. And our predicted base pairs, we now have to write an equation. And so what we got is, you start with equals, and this is 20678 times x, which now this is our x value, right? To the minus 3.503 power. And you hit enter, and it tells us that that is approximately 4,200 kb.
Okay.
And then our other one, which you could just copy this down, and the other one is 648. And because all these decimal points don't mean anything, I'm going to fix that.
Okay.
So those are predicted, and you know, they're a little bit off, because remember we had a, I think we were trying to remember, the entire plasmid was 4,400. So if you look here, we're like rolling around 4,800, but you know, this is not quite as accurate as one might appear. I mean, there are a lot of variables that go along, but we're pretty close. And of course, if you really want to take a peek and just to do another comparison, let's go ahead and take our line here, and I'm going to go ahead and insert just to, and this is just for, you know, conversation's sake. We know that we should have a logarithmic, or could have a logarithmic. So let's go ahead and display that equation again. So if you wanted to check with the rather the exponential function, make sure I get the right one. Okay, you could actually do another equation and say it's equal to 78258 times E of the distance. Yeah. Why did that give us? That gave us too big a number.
You didn't multiply it by the negative decimal.
Yeah, that'll happen. Yeah, it's minus 0.923. Desperate need of new glasses. Times R. There you go. And there you go. So you can see the numbers are close, you know, and they vary kind of where you'd kind of expect out here.
Mm-hmm.
So now, again, we ran through this very quickly, you know, how precise I was in drawing the lines. You know, you can argue either way, whichever one, you know, there are a lot of places where one might find error. But it's this entire piece here that really is the end point, is to be able to see that we're getting approximate base pairs as expected based on the sequence of the plasmid.
Okay.